we were able to extract so much information about the shape of a graph from its first derivative that maybe we should think about if we can extract any information from the second derivative of a function. So suppose that we know the second derivative of a function is positive. What is that going to look like? Well, if the second derivative is positive, we know that that means the first derivative is increasing. But remember, the first derivative is the slope of the tangent line on the original function. So if f prime is increasing, that means the slope of f is increasing. What could that look like? Well, if f starts going down, but its slope is increasing, that means that it's curving this way, right? It's going from a more negative slope to a less negative slope. Or it might look like this. It might, if it has a sort of moderately negative slope, if its slope is increasing, it might increase so much that the slope actually reaches 0 and then turns around and the slope goes positive. So it might look like this. Or if the slope of f was positive to begin with, if the slope increases, it has to get even more positive. So it has to be like this. Well, you can see in these three cases, in each of these three cases, f is sort of curving upwards. And sort of the term of art for this situation is to say that f is concave upwards, which really just means the same thing. It just means f is curving upwards, but for some reason concave is the word that gets used. All right, so that's if the second derivative is positive. What does it look like on the graph of f if the second derivative is negative? Well, if the second derivative is negative, then that means the first derivative is decreasing. And if the first derivative, again, is the slope of the tangent line to f. So if the first derivative is decreasing, that means the slope of f is decreasing. So what would that look like? Well, if the slope of f is negative, like this, and the slope of f is decreasing, then the slope has to get more negative. So it has to the graph has to go down even faster. If the slope is, say, a little bit positive, like this, well, if the slope is decreasing, then it might decrease so much that the slope reaches 0 and turns around and comes back down. Or if the slope is very positive, then if the slope is decreasing, it might decrease just so that the slope is less positive, like this. Well, in each of these three cases, you can see that f is curving downwards. So the term of art is that f is concave down. So just by knowing whether the second derivative of a function is positive or negative, we can tell where the original function is concave up or concave down. So to summarize, for x values where the second derivative is positive, we say f is concave up, so the graph is curving upwards like this. For x values where the second derivative is negative, we say that f is concave down, curving downwards. And also, if f of x changes concavity at an x value, we call that an inflection point. So here's what that would look like. So if to the left of some x value a, if it's concave up, then it's curving upwards like this. And then if it switches to concave down at a, then that would look like this. And you can see this, what makes this spot special is it's a spot where the graph is temporarily sort of going straight. Right? It's going straight as it switches from curving one way to curving the other way. So that's if there's an inflection point because we're switching from concave up to concave down. If we have an inflection point where it's switching from concave down to concave up. So concave down, it looks like bad example. I better not try to join these. So if the graph is switching from concave down like this to concave up like that, you can see again we have a spot where the graph is just for a moment going in a straight line. So that's what an inflection point is. For an example, let's find the intervals where this function, x over x squared plus 1, is concave up and where it's concave down. While we're at it, let's identify any inflection points that this function happens to have. So we're going to need the first two derivatives of this function, so let's go ahead and calculate those. So for the first derivative, we need to use the quotient rule. So derivative of the top is 1 times the denominator, x squared plus 1 with no derivative, minus the numerator with no derivative, times the derivative of the denominator, that's 2x, all over x squared plus 1 squared. Okay, now simplifying the numerator, here we have x squared, here's minus 2x squared, so that's minus x squared plus 1 over x squared plus 1 squared. So there's the first derivative. Now the second derivative, you can tell it's going to be a bit of a mess. Things are kind of getting a high degree here. But, right, don't be intimidated, just use the derivative rules. So quotient, we need the quotient rule again. So derivative of the numerator is minus 2x times the denominator with no derivative, so x squared plus 1 squared, minus the numerator with no derivative, minus x squared plus 1, times the denominator with the derivative. So we have to be careful with the chain rule here. So power comes down, 2 times x squared plus 1. The power up here changes to 1. And then times the derivative of the stuff inside this, which is 2x. All over the denominator, x squared plus 1 squared, which makes it to the fourth. Okay, now we can do some simplifying here right off the bat. There's a common factor of x squared plus 1, so we can get rid of one factor of x squared plus 1 like this. And let's see, other than that, it looks like we can factor out a minus sign in the numerator, and we can also factor out 2x, right? Because there's a minus 2x right here, and there's a minus 2x right here. So that leaves from this piece x squared plus 1, and then this is a plus now, and then 2, this 2 here, times minus x squared plus 1. Okay, and then in the denominator we have x squared plus 1 cubed, so minus 2x. And then in here we have x squared minus 2x squared, so that's minus x squared. And then 1 plus 2, so that's plus 3. All over x squared plus 1 cubed. Okay, so after we simplify, this second derivative function isn't too bad. Now remember, to find where this function is concave up and concave down, essentially what we need is a sign chart for the second derivative. And to make a sign chart, remember the first thing to figure out is where this function is 0 and where it's undefined. Notice that it is there isn't any place where it's undefined, because this denominator here is always strictly positive. Right? It's always x squared plus 1. Well, x squared is always greater than or equal to 0, so when you add 1 to it, it's always greater than 0. So we don't have to worry about this second derivative ever being undefined. So we just need to figure out where it's equal to 0. Fortunately, because this second derivative is a rational function, to know where it's 0, we just need to know where the numerator is 0. In other words, we can clear denominators here. So we get 2x times minus x squared plus 3 equal to 0. And since this is already factored, we can split this up, so we get minus 2x equals 0, or the other possibility is that minus x squared plus 3 equals 0. For this first one, x has to be 0, and then for this second one, x has to be plus or minus the square root of 3. Okay, so for our sine chart, we have, right, there's nowhere where the second derivative is undefined, and it's 0. The second derivative is 0 at x equals 0, at minus root 3, and at plus root 3. Okay, so this splits our number line up into 4 different pieces, and we need to check the sign of the second derivative on each of these intervals. So that the test points that I'm going to use are 2 maybe, that would be a good one, and then, sorry, minus 2. And then minus 1 is right here, plus 1 is here, and then 2 is there. So those are going to be some nice test points. So the second derivative at minus 2, notice that the denominator is always positive here. So really, we only need to know whether the numerator is positive or negative. So I'm not even going to evaluate the denominator. It's positive. And then in the numerator, we get minus 2 times x, which is minus 2, times 3 minus, so I'm doing this 3 first, and then minus x squared minus 2 squared, that's plus 4. So we have negative times another negative. So the numerator here is negative. So this is negative over positive. So this is negative. So on this far left interval, the second derivative is negative. Okay, so now let's try -1, x equals -1. Again, the denominator is positive. We didn't know that ahead of time. And then these terms, so you can see that since we only need to know whether this is positive or negative, we don't actually need to calculate these numbers. So it's -2, so that's a negative, times x, but our x value is negative, so that's another negative. And then this stuff in parentheses is 3 minus 1 squared, so that's positive. So this time, this whole mess is going to turn out to be positive, so greater than 0. Okay, next let's check plus 1. So denominator is positive. In the numerator, we have that -2 out front, so negative. And then our x value is positive this time. And then that stuff in parentheses is going to come out to be positive as well. And so this whole thing is going to turn out to be negative. So that's less than 0. So on this interval, our second derivative is negative. And then finally, at plus 2, denominator is positive as usual. The -2 is negative. This x value is positive this time. And the stuff in parentheses turns out to be negative. And so this whole thing comes out positive. That's greater than 0. So our second derivative is positive here. All right, now that we know where the second derivative is positive and negative, we know where the original function, f, is concave up and concave down. So to the left of root 3, since the second derivative is negative, the original function is going to be concave down. I'll abbreviate that CD, so concave down like this. For the next interval, from minus root 3 to 0, second derivative is positive, so the original function is concave up, so like this. And then second derivative is negative, so f is concave down. And then the far right interval, second derivative is positive, so the original function is concave up. So like this. So putting this all together, the original function is concave up on these intervals from, looks like from minus root 3 up to 0, and also, so union, square root of 3 out to infinity. And it's concave down on the rest of the real number lines. So that's from minus infinity to minus root 3, together with 0 up to positive root 3. Okay, what about inflection points? So remember, we have inflection points wherever the sign of the second derivative changes, wherever the concavity changes. There are only 3 possible places, right? Here, here, and here. And it's possible that at a spot where the second derivative is 0, the concavity doesn't actually change. But in this particular example, at all 3 of these spots, the concavity is changing, right? Here it's going from negative to positive, here it's going from positive to negative, and here negative to positive again. So so each of these is an inflection point. So we have an inflection point at x equals minus 3, at x equals 0, and x equals square root of 3. Sorry, minus square root of 3, not minus 3. Okay, if we look at a graph of this function, we can actually see all these features. So I have a graph set up here. Now, minus square root 3, let's put that on our graph. So there is minus square root 3, and you can see that it's a little hard to see, but to the left of this spot, the graph is actually curving downwards very slightly. It's pretty slight, but it is curving downwards. So we can see that it's concave down on this far left interval. Now between negative square root of 3 and 0, clearly the graph is concave up here, right? It's curling upwards. And in between the two, because it's changing concavity, there's an inflection point. So at this spot right here, the graph is just for an instant going in a straight line rather than curving one way or another. At x equals 0, clearly the concavity is changing again, so it's going from concave up to concave down over here. And so x equals 0 is an inflection point where just for a moment the graph is going straight. And then at square root 3, we again have an inflection point. At the far right, it's a little hard to see, but the graph is curving upwards, and so in this far right interval, the graph is concave up, and that makes this point at x equals square root 3 an inflection point because it's switching concavity.